Welcome. In this video, we are going to implement the great Maxout paper. So that's a paper that was introduced by Jan Goodfellow on his fellow co-authors in 2013. That's also an activation function that was used in the initial GAN paper, but unfortunately, it is not implemented in PyTorch, for example, and therefore you need to implement it yourself. And in this video, we're going to implement it from scratch. That's a very interesting activation function. It has a lot of nice properties. We're going to use it for classification as they do in the paper. On desired results we get by the end of this video. So this is testing accuracy on mixed data using MLPs, no CNNs. And we're going to get an accuracy of in between 1 and 2, well, the test error in between 1 and 2%, so below 2%. So that's pretty nice. Okay, let's dive directly into the implementation. We're going to use PyTorch, and again, it's not directly implemented in PyTorch. I think it's nice to have this implementation so that you can reuse it in other projects. So first, as I've said, we're going to use the MNIST dataset. So we can use the load data function from Keras to load the data. Then we're going to normalize the data between 0 and 1. So we can start and implement the Maxout activation function. So basically what the paper is doing, basically for each hidden layer, we take the maximum value along k. So for each hidden unit, we'll have a proposal of k values, and we take the maximum along the k values. And all those k values are generated. So basically we have MLP. So basically each value will be generated by a MLP. So for example, in our implementation, k will be equal to 4. That means we're going to do k linear projections. And then for each hidden unit, we are going to take the maximum value along the k values, so along the 4 values in our case. It will be much clearer when we dive into the implementation. As you might have understood it, the issue is that then the compute is increased because for each forward pass you need to do 4 times more linear projections than with, for example, using ReLU or other activation functions. But this one also has other nice properties. So basically here we have our linear layer. So basically instead of implementing 4 linear layers on having a loop on doing the forward pass one by one, here we can just do a single linear projection. But instead of projecting to the out value, so basically with a number of input dimension, output dimension, usually we'll just go from input dimension to output dimension. Here we do k times with k times more output dimension, and then we're going to reshape that. So let's do that directly. So in the forward pass, we do the matrix multiplication, net of x, and then we reshape it. Actually this reshaping can be removed. It's useless because it already has that shape. But then basically we can reshape it to have the out on self.k. And then we're going to take the maximum value along those k values. So that's what we're doing, torch.max. And here we're doing dot values because torch.max returns multiple values. It returns both the values on basically the maximum values on the indices of those maximum values, so the argmax. So we're just taking the values. So very simple to implement. On now basically everything else is just like building on top of that, implementing the training loop, the neural network that will have this activation function, and then doing the classification on list. So for training, that's a standard training loop with a model, an optimizer, the loss function we're going to use, very likely the negative log likelihood loss because we're doing classification, number of epoch, batch size, and then the training data, train X, train Y, test X, test Y for computing the testing accuracy during training. If we wanted, so basically here what we did, we are just plotting the testing accuracy as a function of the number of epoch. We can see that we train a bit too much at the end with some overfitting. So basically what will be a better approach than what is done here. So basically a further improvement that could be done is to have a validation data set to do early stopping. So basically we iterate over the number of epoch. We've prepared 2 variables, one for logging the training loss, one for logging the testing accuracy. Basically for each epoch, we're going to iterate over the full data set. So basically we're going to record the batch training loss and then log the average of the batch training loss in the training loss. So basically here we are shuffling the indices of all the training data. And then basically we are going to chunk, so basically to process all those indices, we are going to chunk them into batches. And therefore here we fetch the training data at the proper indices that have been shuffled. That's important to shuffle them after each epoch. So yeah, we sample the data, we reshape them. The data are 2D because they are images, but we are processing them with MLPs. So we reshape them as a 1D tensor instead of 2D images. So with the input and the output, we compute the log probability that the model assigns to the input, and then we compute the loss function between the log probability and the real target data. Then you can do a gradient step to update the model weights. And then yeah, just logging. So we log in the training loss, we log the mean of the batch training loss so that it's smoothed it's better than just having a look at the than just directly here logging the loss to the training loss, because it will be very noisy. So we just have a look at the batch training loss, which is average over the full batch, over the full epoch. Then you can do testing. So let's not forget to put the model in testing mode. For example, if we're using dropout, that's very important. On here we do the same. We compute the log probability that the model assigns to the testing data, and then we compare the argmax. So basically to which class the model assigns the most probability, and we check if it matches with the target label. And then we can just return the training loss on the testing accuracy. And that's almost already done. Now we can put everything together. So again, k is the number of k is the hyperparameter, which will be the number of linear projection we do, and for which we take the maximum value out of them. Then we train for 50 epoch. Again, that's a bit too much for that task, but we cannot use that curve to find the best amount of epoch, because then that will be not cheating, but basically we should never use the testing data to find the hyperparameters. We should use some validation data sets. So yeah, if we wanted to improve this code, we should add a validation data set to stop at the proper when the validation curves do not improve. We use a batch size of 128, and then you can create a model. So basically we're using model with dropout. Basically they describe that in the paper. Then Maxout, dropout, Maxout on logsoftmax. So basically here the sequential, well, not the sequential, but the MLP is embedded in the Maxout class. So basically Maxout at the same time does the linear projection on the non-linear activation function. So we don't need to put a linear layer and then the Maxout, because the Maxout already does the linear projection. So once we have the model, we can create the loss function. That will be the negative log likelihood loss. The optimizer, we're going to use Adam with weight decay. And then you can call the tuning loop to train the model. Finally, you can plot the testing accuracy to reproduce the figure we've seen previously. And we use Seaborn just to get more, like instead of matplotlib, that will be like a figure with a white background. Here it looks a bit more scientific. But yeah, that's just a design choice. So we use Seaborn that is built on top of matplotlib. And then we make a plot. We plot the number of, the testing accuracy as a function of the number of epoch. We set the X and Y labels, and we save the image. So I hope this video was helpful to you. Please leave a thumbs up if it was the case. That's really helpful for this channel. Subscribe for more content related to machine learning, and see you in the next video.